Good morning, my name is Braña. I'm going to talk about the development of a power transformer model to predict high-frequency transient phenomena. This presentation is divided into several parts. First, I will describe the transformers in the electrical network. I will introduce the white box modeling for power transformers, the experimental test that I have used to validate the model, the results that I have reached with this model and the simulations, and finally, I will present the conclusions that I have got. In recent years, the proliferation of distributed renewable energy sources and applications of new rules for the exploitation of the networks have increased the demanding operating conditions for power transformers. These elements, in addition to the electrical network, are the most important and critical element of the power system. The transformer isolation is the critical element of design, and it is exposed at very high frequencies to transient phenomena as lightnings or switching maneuvers. Although there is a great knowledge of the transformer behavior at rated frequency, 50 or 60 Hz, it's not the same for very high frequencies. So the development of representative and reliable models for this frequency band is necessary. The transformer manufacturers make use of the tile models. Inside these models, we have the white box modeling, which its main concept is to represent the transformer topology by means of passive elements in an electrical circuit. These elements are resistance, capacitance, and inductance, and they have a physical meaning and calculated from the geometry. This type of models can be classified as lumped parameter models, distributed parameters, models which follows the electromagnetic wave theory, and electromagnetic field analysis. In this work, I have used a lumped parameter model. In the model, every winding is constructed by cells, as they're represented here. This cell represents a geometry like a group of turns, a group of disks, a single disk, depending on the accuracy that you desire. We can see passive elements are this resistance, which governs the damping on the waves, a resistance which represents the ohmic losses, the inductance, the series capacitance, and the parallel capacitance, which couples the different windings. The parameters are constant and were calculated for a frequency above 10 kHz. This value is mentioned by some authors that consider that above this value the magnetic core can be neglected. As we can see here, the transformer, all the cells are linked together. And here I try to approximate the geometry because in the reality I have a lot of more cells, but for this picture it's difficult to represent all. So in this case, we have at the left the tertiary winding, then we have the low voltage winding and the high voltage winding. They are linked in series, all the group of turns, and we have parallel capacitance, which represent the capacitive coupling between the windings. The model has been validated with our reference transformers of the Cigré working group, This transformer is a 3-leg transformer, core type, medium power, and the transformer is built with a tertiary winding, low voltage winding, high voltage winding, and regulating winding. As we can see here, you can notice that despite being a one-phase transformer, the core is a 3-leg core type. The windings are in the middle limb, and the return flux is in the other 2 limbs. The experimental tests are voltage transfer measurements. This is a modern technique developed by Björn Gustafsson some years ago, and basically consists on, well, simplifying this a lot, applying some volts, maybe 10 volts or even less, to different points on the transformer, and with a procedure of vector fitting with the response, you can construct the response of the transformer to any wave that you desire. So for this transformer, different test configurations were tested, like applying voltage at one point, grounding in another point. In this work, I just will show 4 cases just for a sample. In this slide, we can see the typical impulse voltage wave that is applied in the impulse test. In this case, that is the wave that is applied once the vector fitting has been executed. So we can see on the left the wave, and on the right the configuration for case 1. You can see that the tertiary winding and the low voltage winding are ground. The wave is applied on the high voltage winding at each one point, and we measure the response on the regulating winding. These tests, as I said before, are high frequency tests, and this model wouldn't work at a rated frequency at 50 or 60 Hertz. And here we can see the results that I have reached. In all cases, the correlation was quite good from the transformer manufacturer prospect, because the amplitude values of the wave for the measured wave and the calculated wave were very similar. The phase correlation of the waves was not so good. You can improve the phase adjustment between the waves, modifying the value of the parallel resistance, that is the component which governs the decayment and the damping of the wave. That resistance is a mathematical value or multiplied by an empirical factor. So you can, with more cases, you can try to calibrate this value. Here we have 2 other cases. In case 49, results were very similar. In case 33, were not so good. Anyway, I mean, I could show best cases here, more or less. I took the average. I have better cases. I have less better. Results can be improved reviewing the capacitance calculation, especially for the interleaf winding, which was the high voltage. Normally, in the capacitance calculation, you try to be conservative, but in terms of amplitude. But in terms of phases, you don't pay a lot of attention to that. Another uncertainty that you have is that, well, ideally all the parameters should be frequency dependent, but for simulation purpose, this is difficult. This increases the calculation time, and it's not so easy to change in the time domain, change the value in function of the frequency. Another typical uncertainty could be because these tests were taken with a transformer not immersed in oil, just with air, but some materials, as the pressboard or paper of the isolating structures, could be in impregnated oil in air, which is not the same. So the permittivity value changes a bit. But anyway, in general terms, the correlation was quite good. Finally, for the conclusions, we have seen that a white-box model approach can accurately simulate the response of the high-frequency transformer response, especially from the transformer manufacturer perspective. We have seen the potential of this non-standard input test that has been used for obtaining the voltage response. This approach is very useful for calibrating the simulations and transformer model tools and this stuff. Anyway, obviously the results can be improved, and several actions we can take, as I said before, reviewing the capacitance calculation, ideally make some parameters frequency dependent, or recalibrating the value of the parallel resistance, which governs the decaying of the wave. And this is the end of the presentation. Thank you for your time and attention. I remain to your disposal for further explanations and questions.